In today's lesson, we'll be verifying trigonometric identities. In mathematics, an identity is an equation which is always true. It could be something that's trivial, like x equals x, or more useful, like the Pythagorean theorem, a squared plus b squared equals c squared, helps us to solve right triangles. There are many trig identities, but the following ones are the ones you're most likely to see and use. The ones we'll use today are the basic and Pythagorean theorem identities. But some of the ones we're going to be exploring in the next week or so are the angle sum and difference, double angle, half angle, and the sum and product. If you look back at this lesson, you will notice that I have provided you with a Google Slides in order to help you refresh your memory for some of these basic identities. For example, the reciprocal identities, the quotient identities, the Pythagorean identities, and some variations on how to write them. And these will be very important. 1 minus sine squared of x is the same thing as cosine squared of x. And the same thing with 1 minus cosine squared x is the same as sine squared x. And finally, the odd and even identities. Now, how do we go about verifying trigonometric identities? Well, here's some of the things that we might do. And you probably should write these down in your notes in order to help you think about this for each problem. Number one, work with one side at a time. We also want to keep in mind that both sides need to be exactly the same when we're finished. We can start with either the left side or the right side. It doesn't matter. And finally, consider that you may want to use some algebraic manipulations or some of the basic trigonometric identities to help you have the same expression on the left and right sides. Let's look at a quick example. In this example, we have the equation cotangent x times sine x equals cosine x. And we want to verify this identity, meaning we want to make sure that the left side and the right side are equivalent. They are equal. So what can we do first? Well, notice that we have cotangent x. We can rewrite that in terms of sine and cosine. This is the same thing as cosine x over sine x. And if we rewrite that, then we can see how the sine x and sine x can eliminate. And all we're left with on the left is cosine x, which in fact is equivalent to the right side, which is also cosine x. We have now verified the identity. A couple other things to keep in mind. Always start with the more complicated side. Also, try substituting basic identities. For example, changing the functions to be in terms of sine and cosine may really help things be easier. And then try algebra. Factor, multiply, add, simplify, split up fractions, combine fractions, whatever will get you to making those two sides equivalent. And if you're really stuck, make sure to change everything on both sides to sine and cosine. And then the key is, remember, work only with one side at a time. Let's try our first identity. Here we have sine theta times cosecant theta minus cosine squared theta equals sine squared theta. If you like, go ahead and pause the video, see if you can establish this identity on your own, and then we'll work through it together. Okay, now what would you do? If I'm looking at this identity, I'm saying, well, the left side is definitely more complicated. I also have cosecant in here, which I can change. So let's go ahead and switch cosecant theta into its reciprocal of 1 over sine theta. Now, just like the previous example, I can see where sine theta times 1 over sine theta simplifies into just 1. And now on the left side, I have 1 minus cosine squared theta is equal to sine squared theta. Anytime you see cosine or sine that's squared, you should immediately think about the Pythagorean identities. We can rewrite 1 minus cosine squared theta as sine squared theta. If you need help remembering, go ahead and write out the main Pythagorean identity on your paper, like this. When you have it written out, it's easy to see how you can change this around through algebra to make it look like 1 minus cosine squared theta. If I subtract cosine squared theta from both sides, then I can see that on the left side, I'm left with sine squared theta, and that is equal to that 1 minus cosine squared theta, which is what I just substituted here to be sine squared theta. And now we've proven this identity. The left side does in fact equal the right side. Down here we have a key note that you should think about. In establishing an identity, you should not move things from one side of the equal sign to the other. Instead, substitute using identities you know and simplifying on one side or the other side or both until both sides match. The key is do not ever move things from the left side to the right side or from the right side or to the left side. You would only do that if you were evaluating or solving an equation. But in this case, we're just verifying identities. We're verifying that what we have written on the left does in fact equal what we have on the right. Let's try another example. Again, try this one on your own, and then come back, we'll do it together. Now our equations are getting a little more complicated. But when I look on the left, I see cosecant and cotangent, so I'm going to go ahead and start there. I'm going to change those. Cosecant is 1 over sine, and cotangent is the same thing as cosine theta over sine theta. So I followed my advice. I changed everything to cosine and sine. But now I have I have two fractions. Let's go ahead and combine our fractions. We have 1 minus cosine theta all over sine theta. I had a common denominator, so I was able to combine my numerators. But this still does not equal this. Well, one of the tricks we can do that we talked about was using algebra. We need for our denominators to be the same. But we don't have a Pythagorean identity situation here because nothing is squared. So let's go ahead and look at the right side. I can't really do much with sine theta, but can I change 1 plus cosine theta into a sine somehow? I can if I multiply by some kind of fraction of 1 or some kind of factor of 1. So one of the tricks that we use here is to take and multiply by the conjugate. The conjugate of 1 plus cosine theta is really 1 minus cosine theta. And if I do this, I can end up changing this into a Pythagorean identity because I'll have a squared, and I can perhaps change it to be sine and maybe get close to this left side. Once we do this, we want to multiply. So our numerator will be sine theta times 1 minus cosine theta. And our denominator, because these are conjugates, I can use the shortcut. First term squared, so 1 times 1 is just 1, minus second term squared, cosine squared theta. Or if I'm more comfortable foiling these, I can do that as well. Now we just saw from the last problem that 1 minus cosine squared theta is the same thing as sine squared theta. So what I can do is replace this denominator with sine squared theta. And now when I look at my right side, I can see that I may be able to simplify this a little bit. What I can do is I can reduce my signs. This sign can cancel into one of these. And what do I have left on the right? 1 minus cosine theta all over sine theta, which is what I ended up with here on my left. I have now verified that identity. Let's try yet another. Again, go ahead and pause and see if you can do this one on your own. For this one, because they're both fractions, I'm going to go ahead and simplify the one on the right because I have secant in here. So let's replace secant with 1 over cosine for both the numerator and the denominator. Now I have a situation where I need to combine and make one fraction for the numerator and one for the denominator. So instead of writing 1, I'm going to write 1 as cosine theta over cosine theta. Now that I've replaced my 1's with cosine theta over cosine theta for both the numerator and the denominator, I can now cancel out all my denominators because they are all the same. So what am I left with? I'm left with cosine theta plus 1 over cosine theta minus 1. And now I know that the right side does in fact equal my left side. How about this one? In this situation, on the left side, I have two fractions that need to be combined. Even though my right side looks like maybe I should change tangent and secant, my left side is more complicated because of the dual fractions. So in order to combine these, I'll need to get a common denominator. I'll need to use both 1 minus sine theta and 1 plus sine theta as my common denominator. The next step will be to go ahead and simplify all of this. So what do we have? We have two of these that we're multiplying. So let's write this as 1 plus sine theta squared minus two of these, 1 minus sine theta, again squared. And then how about our denominator? Well, we have 1 plus sine theta times 1 minus sine theta. Now I'll need to go ahead and FOIL and distribute the negative into the parentheses once I FOIL in order to combine my like terms up top. Let's go ahead and do that. We can use a shortcut whenever we're FOILing an expression twice, and that would be first term squared, first times second times 2, so that's going to be 1 plus 2 sine theta, and then last term squared. So that would be plus sine squared theta. Minus, and notice I'm leaving the parentheses because I'm not ready to distribute the negative in yet. So let's go ahead and FOIL the second set, or the second expression, the same way. Now that I've FOILed this, I'm ready to distribute the negative into the parentheses. So let's come over here and write what we have. We have all these terms, and then we have minus 1, then plus 2 sine theta, and finally minus sine squared theta. Now let's FOIL the denominator. Again, we have a conjugate, so we can use a shortcut. We can do first term squared, which would just be 1, minus second term squared, which is sine squared theta. Now we're in a position where we need to combine like terms. So let's see what we have. I can see right now that 1 minus 1 eliminates, and sine squared theta minus sine squared theta eliminate, and we're just left with 2 sine theta plus 2 sine theta, which we know is 4 sine theta. And then we can look at our denominator here and see that 1 minus sine squared theta is the same thing as cosine squared theta. The reason that I changed this is because look back at the identity. Think about what we're trying to get. We're trying to get tangent and secant. Well, tangent we know is sine over cosine. So we need to change the denominator to be a cosine, and now it is. But how can we make this look like 4 tangent theta secant theta? Well, sometimes this just requires us to separate some things out. So let's go ahead and try that. Again, we're going to come over here and we'll separate the 4, and let's take a sine, or the sine that we have, and put it over one of our cosines because that'll make a tangent. But then what do we have left? Since this was cosine squared theta, we still have a cosine left. Here's what I get. Now let's see. We can replace sine over cosine with tangent, and we can replace 1 over cosine with secant. And now, in fact, if you'll notice, we have proven this identity to be correct. We have verified it because this side, 4 tangent theta secant theta, is now equal to our left side, 4 tangent theta secant theta. And that concludes our lesson today on verifying trigonometric identities. So remember, don't get discouraged. Every identity is going to be different. There's no right or wrong way, just best practice. Keep trying different approaches. The more you practice, the easier it will be to figure out efficient techniques. And if a solution does elude you at first, sleep on it, try again the next day. Just don't give up and you will succeed.